For those of you who've never been to the Marilyn Observatory, we have a fairly, a little bit over 50 years old. It was built in 1964 facility. It has, it's a roll-off roof observatory with an East Bay, central office area in the West Bay. We've got several telescopes over there. Some of them are permanently mounted, and then we also have lots of portable telescopes, which we're going to ignore. We're going to be focusing on some of the work we've done with the telescopes that we have in the East Bay. So those are the 3 telescopes, a 14-inch Schmidt-Cassegrain, and then 2 refractors there. So all these telescopes are pretty much commercial telescopes with all fairly straightforward parts that are commercially bought. And so this is our 14-inch Schmidt-Cassegrain. It's on an AP 1200 mount, and that's probably going to be one of the most important things about the telescope, is having a good mount to move the telescope around in the sky. We have SBIG, Santa Barbara Instrument Group cameras. This one has the ST8 camera. These are older models, but they are fine for what we need to do. Plus, we have them. We don't have to buy anything new. I dread the day that they break and that I have to get new cameras, because that'll be interesting. These do have 10-cell filter wheels associated with them, and we do have some RGB as well as narrowband and a couple of photometric filters in this particular telescope. There is an auto guider on there as well. Next summer, one of the things that we're planning on doing is installing a motorized focuser and rotator system on it. We also have a refractor there. This one's also on an AP 1200 mount. A number of years ago, one of our faculty retired, and he very graciously, permanently loaned us his traveling kit for observing comet occultations. He had brand new, still in the box, mount here and a 14-inch telescope. We immediately put the mount to work and converted the mount from the old point and yank and point type mount to have this AP 1200 so that we could actually use the telescope. The telescope OTA was AP refractor. It's nothing to sneeze at, but we couldn't use it for science beforehand. It was just visual observing. But we were able to improve it by having the new mount. It has an ST10 camera on it, much bigger field of view. Also a filter, 10-cell filter wheel with a few narrowband, a couple more photometric filters as well. Also an auto guider, and we'll be installing the motorized focuser on it over a winter break probably. This one is actually my telescope. We actually don't have enough telescopes for students to do research, so I brought one of mine in and kind of have it sitting in there, and generally use it as a test bed for different things. It's on a 900 mount, 10-cell filter wheel. Has an auto guider, and I've been testing out the motorized focuser on that one to understand how it works so that we can put together a good instruction manual for the students. But the different filters in the telescopes kind of dictate a little bit of what we can do with each one of the telescopes. And the other important thing is sort of the fields of view of each one of the telescopes. So the innermost box here is the field of view of the 14-inch telescope with the ST8 camera. The field of view right here is the 7-inch with the ST10, and then the outermost box is the 6-inch with the ST10 as well. For a short time, the camera on the 7-inch had broken, so we had to borrow a camera from another instrument. And we had a really tiny field of view. We were very frustrated, and for a year we were kind of getting by, but everybody was like, let's get the camera back, because we wanted the field of view. We have some other instruments. We have an occultation system, basically a kit that includes a camera, a GPS system, and things like that. And it basically is an eyepiece camera, so it sits in place of the eyepiece, so I don't have to switch too much gear. And then we, a couple years back, found a Santa Barbara Instrument Group spectrometer, and we've been working on trying to figure it out, get it running, and we hope to eventually put that onto the 20-inch. We had to put that on hold, though, because this is where we had to borrow the camera from for a short while. So the research that we concentrate on at this observatory it's aimed at the undergraduate students. And so we're trying to give them a hands-on experience with the telescopes and the cameras, the data collection from beginning to end. And so they kind of get the whole process. And there's a lot of non-majors, so they're not necessarily astronomy geeks. They're non-majors, a lot of them. We have some high school students usually. Occasionally we'll have some independent study students. Those are usually majors though. And most of the projects that we've up till now have been focusing on are photometric in nature, where we're trying to measure the change in brightness over time. And so you get a nice little light curve out of it. And so that's sort of the goal, is get some good light curves. Show what is happening with this object. And so that means that we can observe exoplanet transits, we can observe binary and variable stars, we can do some supernova work. Students could potentially do asteroid rotation, and then we also do occultations. But because of the filters that we do have, we could do some narrowband type projects, and eventually we're hoping to get into spectroscopy as well. A little bit of a side note. Software. Most of the data acquisition is done with a software called MaxMDL, and so no matter what project they're doing, they're using this MaxMDL to collect the data, to actually get the raw data that they're going to be using. But then there's data analysis, where you sort of process the data and analyze it. We've been using AstroImage-J. It is software that is very good for doing differential photometry. It is specialized towards exoplanet transits, but we can use it for the other types of projects as well. And because it is for freeware and it is available on various platforms, so Mac, PC, everything, it's easy to deal with. However, there are other programs that are specialized, and as we start moving towards some of the other projects, we will probably start having to invest more into those. And that makes it a little bit tough. I'm trying to do a little bit of everything, whereas most amateurs will usually focus on one of these projects and become an expert on it. So you wouldn't necessarily have to have all of these programs. You sort of pick one of the projects and then you go for that specific set of programs for that project. We do have PhD for guiding. Next thing I'm looking into is software for the focusing and potentially some automation stuff that would affect a couple of the projects. One of the things that we go through with the students is that pretty much all of the projects have roughly the same procedure. They have to do an initial prep of figuring out what they're going to look at, preparing star charts, figuring out what do they need, what data do they need to collect. At the observatory, they have to do all the equipment setup, finding the target, which is harder than it seems sometimes. They have to take some test exposures to figure out what is the right exposure for their target. If it's a brighter target, they may have to do shorter exposures. If it's a dimmer target, they may have to figure out a longer exposure. So they have to figure out a good exposure. They then sort of build some imaging sequences to collect the data. They have to do some sequences for collecting calibration data as well, to calibrate their science frames. Afterwards, there's the actual processing of all of that data, calibrating it, and then analyzing it. Again, we generally do mostly differential photometry stuff, so they have to do that processing, graphing, putting it into a poster eventually for presentation at the end of the semester. So they kind of have to do some kind of submission. I took over the University of Maryland Observatory in 2002. The observatory was sort of considered to be a undergraduate teaching and primarily outreach type facility. We hadn't been doing much research at all. In 2011, a student came up to me and said, I want to do exoplanet transits. And my response was, not in a million years, not with our equipment. And he went off, and at that time, the only telescope that we really had set up to do any kind of research was the 14-inch. And he started doing it, but the field of view wasn't big enough. He didn't have enough other stars showing up in the frame for him to do the comparisons against. So that was kind of when I brought in my 6-inch telescope, and even though it was considerably smaller, it had a much larger field of view, and he did it. So this is one of his light curves from way back then from an exoplanet transit. Now, not only did he observe this, he ended up writing his own Python code, which I would love to say that we're still using, but unfortunately he never finished it. Okay, so he was a undergraduate student who was interested in doing stuff. He was working on this code. He did an internship at Goddard, and then he got into grad school, and he's still in grad school in Washington State. So this is sort of a side project at this point. Eventually, I hope he finishes it because it would be a cool program. But at about the same time that he was doing that, I learned about this other program called AstroImage-J, which was already fairly well developed, and we've been using that instead for the exoplanet stuff. But all of our research kind of started with that challenge, and basically I learned that, of course, you're not going to be able to get anything if you don't at least try. So if you're interested in doing research, go for it, okay? The only thing that can happen is you don't get data, okay? Since then, we have focused on exoplanet transits. We've gotten, I feel, quite good at this. We start the students usually observing known exoplanets from the Exoplanet Transit Database, which is a Czech website. And so you can actually find the predictions of when transits are going to occur. So we have the students observing those first. And they observe those, they run it through the processing and everything like that. And since we know there's supposed to be a transit, they should get a light curve out of it. If they don't get a light curve, then we know that they either tagged the wrong star, they did something else wrong with the processing, or something else went wrong, okay? And so we try to debug that, and then once they get comfortable using the software and everything and doing stuff, then we actually move them to unknowns. We recently, late summer 2016, joined the KELT Fund, the Kilodegree Extremely Little Telescope Follow-Up Network. It is, as he was mentioning, sort of one of these systems where they have multiple smaller cameras. They have one northern hemisphere and southern hemisphere, basically does surveys, and somehow they get a collection of potential targets of a star. This might have an exoplanet around it, but they're not sure. And so they farm out these potentials to their follow-up network. And so we're on that follow-up network, so we have access to that little database, and we can go in and observe those as well. And basically, people either confirm, yes, there is an exoplanet there. It was on time, or it was early, it lasted longer, it lasted shorter, whatever the case may be. Occasionally, sometimes they give us bad targets, and it turns out that it's actually a binary star, some eclipsing binary is in the same field of view, giving a spurious signal. So all of these are for different exoplanets. What you're usually looking for is the blue dots is usually the data, and there's a best fit light curve here. All of the little lines and dots down here are from some of the comparison stars, and you're usually comparing your brightness of your target star against sort of an average of those comparisons. And so you can kind of clearly see a nice little exoplanet type dip in those. Here you see it as well. And then over here, there's no dip here at all in the target, but one of the comparison stars, oh look, something's interesting happening there. And so you can report that back and say, target comparison star X is actually looks like a binary. And so you can send that back in as well. We've observed about 25 of these so far, and we've submitted for reports back on about 10 of them. So we've kind of gotten pretty good on exoplanets, but we do observe or have students that observe a couple other things. One of the reasons that the students like to do the exoplanet transits, or why I like to do them, is there's sort of a finite set time of when they happen. So you can actually see when one starts and ends, and so you can sort of schedule yourself to observe for that time period. Okay, it's not sort of a vague, I just have to observe all night. You can sort of say, I need to be observing for this time block. And so it's a little bit easier to mentally schedule. Some of the other projects require a little bit more of a vague, I just need lots of hours. Okay? We do observe binary eclipsings and variable stars as well. We use the same software, that Astroimage J, to do the processing, and it pretty much gives you similar types of stuff. If you are interested in getting into binary stars and variable stars, the best place to start is the AAVSO, American Association of Variable Star Observers. This is one of the premier amateur research organizations. They kind of start off with the variable stars and eclipsing binaries, but they kind of do a lot of other things, including exoplanets as well. They're sort of building up their own database for that as well. But they have a lot of basic information on how to get started in doing photometry, how to measure the brightness of things. And they have classes, online classes that you can take if you're a member, and it's a really good way to get started, to get familiar with some of the different projects. So AAVSO is kind of the best way to get started there. Fortunately, all the pretty graphs that the students have taken are sort of embedded into their posters, and I don't have any of the separate graphs, so I don't have too many nice ones to show. But let's see, supernova. This one's a tough project to do, mainly because most supernova searches usually operate in sort of an automated fashion, where you can actually tell your telescope, go to this target, that target, that target, that target, and just runs by itself during the night, takes some pictures, you kind of have some comparison images to detect them. We're not really set up that way. We don't have that automation yet. Sort of the wish list item for to maybe do that one day. So we allowed one of the students to do sort of a follow-up, and the idea was that could he get enough of the light curve to be able to match up the identification, the type of supernova with, from his observations, and would it match up with sort of the known types. And unfortunately, he didn't observe as much as I would have wanted him to, but he did get just enough data, and so he's got a couple supernova here, and one of them he's got enough data where you just sort of have this nice little fading and brightness here. This one has a little bit of fading, but then it starts to get bright again. And so when you sort of look at the types, these are the different types. The fading on this one is just kind of gradual enough that it sort of matches up with some of these ones that are gradual. And the one with the little dip, it matched up to actually that type of supernova type. And so he actually did get just enough data to sort of show it. And he didn't observe all that many months. I would have wanted him to observe a little bit more often and a little bit longer, but sometimes you only have the students for a semester, and not as 3 years. That would be maybe ideal for some of this. There are some websites that give a lot more detail about getting into supernova searches with amateurs. The Backyard Observatory Supernova Search is one of the groups. There's also a group over in Europe that does supernova searches, and they have a lot of details on their website. You can actually get lists of currently observable supernova from one of the New York clubs, as a list of current supernova as well to follow up on and such. Now this is one that's done by a lot of amateurs. They actually do asteroid rotation. The idea here is that asteroids are not spherical. They're going to be more potato-shaped. So as they're rotating, they reflect different amounts of light. And so if you can determine their rotation rates, that kind of gives you some limits as to how they're put together. If they're spinning really fast, then they have to be more solid than rubble piles. If it's a rubble pile and if it's spinning too fast, the rubble pile will fly apart. So by knowing the rotation rates, you get some limits on how the asteroids are actually put together. Right now, this particular project has mainly been done by non-majors using some remote telescopes, eye telescope and a couple others, and they actually fold data from multiple nights and multiple observers into a light curve. And the software allows them to fold the observations from different nights, and does some scaling and such until they kind of get a best fit little rotation rate. Part of that class is to not only do the observations and process the data, but then they actually have to write up their results and submit it back into the Minor Planet Bulletin, which is sort of the peer-reviewed publication of light curves. And so pretty much it's primarily amateurs, but it is peer-reviewed. The data does get archived in the NASA Planetary Data Systems Small Bodies node, which is at Maryland. And so I have seen this data collection, so it gets officially archived. Highlighted here are basically the observations from last spring, that were just published in the last issue of the Minor Planet Bulletin. This effort of collecting all of the asteroid light curves is spearheaded by an amateur, Brian Warner, no relation. He's out in Colorado, and he's been doing amazing work, but he is technically an amateur. And he spearheaded this project and has really moved it forward. He is close to retiring and is basically handing off his website and all of the stuff to the Minor Planet Center. And so they'll be taking over some of the functions that he's been doing, because the professional community recognizes that this is a resource that we cannot lose. Okay? But the data that goes into it is basically furnished primarily by amateurs who are out there observing asteroids. And it doesn't take very big equipment. So there's a nice little light curve that they collected. Again, we haven't quite done that just because it's hard to convince students to go out and observe on a vague number of hours. So they're less inclined to do that one at our facility. Another one that we haven't really tried yet is to do astrometry, where you're measuring the positions of asteroids. And again, this is really primarily, a lot of amateurs do this work, where they actually go in. The Minor Planet Center actually has a list of newly discovered objects, and they rely on observers, lots of amateurs, to do follow-up observations, to kind of go and observe these targets for multiple nights so that they can refine the orbits of these objects, so we kind of know what it is. A couple of times they will just count an object as being space debris. Sometimes we find that it's going to fly really close. Sometimes we think it's going to fly close, but further observations show that, nope, not going to fly so close. And so they need timely observation. So a lot of these come out, and they're relying on amateurs to basically be able to go out and observe as soon as they can. Okay? Professional astronomers don't have that flexibility. The professional telescopes, all the really big telescopes, are already spoken for and have specific projects that they're working on. So they don't always get to just do anything that they want to. Amateurs can. And so there are amateurs who basically, this is all they do. Every night they go out and they're doing follow-up observations on asteroids and getting astrometry. And so there's a whole bunch of information on the Minor Planet Center website, Brian Warner's website as well, the Minor Planet Observer. He's also got a lot of information there as well. In fact, they reference him for some of their stuff. So small body astrometry. Not just asteroids, but also comets. Let's see. All right. So occultations. This is one of my personal favorites. It takes much longer to set up and take down the equipment than it does to actually make the observation. The observation takes all of 5 minutes, if that sometimes. I actually did an undergrad project on grazing lunar occultations where I traveled all over the state of South Carolina observing lunar occultations. And so I kind of had an interest in this for a while. And we had an opportunity some years back to purchase some equipment, and did so, and we've been kind of doing occultation. Two main types of occultations. One is where you have an asteroid in our solar system is moving around the sun, and from our point of view, it blocks a star's light, and it thereby casts a shadow onto Earth. And if you are in different parts of the shadow, you will see the star disappear for different amounts of time. And if you get each one of those observers to report how long the star disappeared for, then you have an estimate of how big that asteroid was. Okay, so you need observers kind of scattered across the shadow path, as well as outside of the shadow path, to give you some limits on the sizes. So for this particular one, the dotted line represents the predicted center line of the shadow. So these folks up here were kind of expecting to see an occultation. They saw nothing. This guy, the orange guy down here, he probably expected to see a miss. But he did see an occultation. We can kind of see how the asteroid, the path got shifted a little bit relative to that center line. Okay? Maybe they were assuming, because they didn't know enough about the asteroid, that it was sort of spherical, and so they were using at that time what they knew best about it. And maybe we were seeing one end of it rather than a long side. We may have been seeing a short side of it. So who knows what was happening. But basically, amateurs do these observations. The other one, which is several people still do, watching as the moon passes in front of a star, and when the star is near the edge of the moon, you can see it disappearing and reappearing from behind the mountains and valleys of along the moon's edge. And again, you get different observers. One observer may see this path for the star. Another observer may see the path where it disappears completely, except for this little part where it blinks in and out very quickly and then disappears again. Another observer may be way up here, maybe sees it briefly disappear here and then reappear. And so again, by having lots of observers, you kind of get a profile on the edge of the moon. And this was much more important before we had some of the spacecraft that did the orbits around the moon here in the last couple of years. So this was a big push during the 70s and 80s to kind of really get occultations, grazing lunar occultations done. Because of the equipment we have, we're focusing mainly on the asteroid occultations. And it's actually a lot of fun because it's a very dynamic type of event. We prepare for it in a lot of the same ways. Creating a star chart, trying to find the target star. This is just a raw image from one of the cameras. And because we can actually use the telescope, and this goes in place of the eyepiece, we can leave the regular camera on there and use that for finding the star field. And so here you see one of the images in all its gory rawness with dust spots and all kinds of issues. And then after processing, basically we take a short video, and then we process the video through a program called Tangra. And it's not easy, but there's a little dip right there. The teal is our target star. When we kind of zoom in on it, it's very obvious. There's a drop. The light from that star dropped out for a couple of fractions of a second. And we are using a video system because we are talking about fractions of a second for most occultations. Some occultations can last a little bit longer, a couple of seconds, but most standard CCD cameras with the exposure rates and the download times just aren't really capable of them. So the newer astronomy video cameras, which are low light, high sensitivity, but they're video cameras, is really good for this occultation work. Now the big things is having a good GPS or a good way of having not only your location really well marked and a good time signal, because that makes a big difference on how it gets folded in with everyone else's data. So these are some of our attempts. Again, we report the data back to the International Occultation Timing Association, and they publish it on a website. And then each year they collate the data, and again, because it has to do with asteroids, they actually submit the data to the Small Bodies Node, to the Planetary Data System Small Bodies Node, so the data gets archived there as well. And any data that goes into the Small Bodies Node is peer-reviewed. So this is another way of getting published as a student. So we've had some pretty interesting ones. We did participate in the Quaoar occultation, but we got a negative. We've tried for Pluto a couple times, but the most recent one was too cloudy. And Ricardo was kind of the last clear night that we had. Unfortunately, they don't happen on the clear nights. There's always a little knot of occultations that never fails us when we have the cloudy nights. Correlation in the past month and a half has been amazing. It is a portable system, so this is where I have set up in Colorado. I basically took my little Orion short tube with me. It's a little eyepiece camera sitting on the back. There's a little laptop, and there's like a little GPS unit that I carry with me. It all fit into my baggage. I keep a camera tripod out there. I'm going to have to carry that back and forth. And so we're just set up, but as you can see, clouds. And it was a little bit breezy, so that night was not particularly good for having sort of a flimsy tripod like that. Here's another one. It was on an equatorial mount, but it was not actually tracking. There was no motor on it. And so we just sort of set up equatorial, roughly pointed it. This was down along the Potomac. This was the Ricardo occultation in August. And so it's just a little, fairly simple little setup. Now some other things that we're trying to get into that we're going to be trying out, like I said, we have this instrument that we found, so we need to get it working, and we hope to install it on the 20-inch. This will allow us to do some spectroscopy. Now, a simpler way is we have a grating spectrometer, which is basically just a filter. And because we can actually put that filter in that filter wheel, which is what I've done, we have it in the filter wheel. We can actually just use it with our regular cameras. And so there's a website, RSpecAstro, and it's a great website for learning about spectroscopy and doing amateur observations. He's actually got 2 filters. One of them is the SA100, and then there's the SA200. Basically, it's just how much the light gets spread out across the chip, like what kind of field of view you have. So I originally tried the SA100, but it was too compact, and so I switched into the 200, and this is what the 200 is, a little bit more spread out. So here's your star, here's the spectrum from it. I haven't processed this yet. This is sort of the raw data, but if I process it through, you get sort of this, sort of the normal squiggly line that you would get when you see spectra of objects. Now what's kind of neat is that I was just playing and I pointed it at the Ring Nebula. And for those of you who know what the Ring Nebula is, it's a planetary nebula. And it's got it's got some primary emission lines. It doesn't have a continuous spectrum. So it's not entirely surprising that you get sort of just 2 images, sort of the 2 primary emission lines. Okay? And if you really look at the shapes of these 2 and the sizes, they are different. So it really is pulling out some of the detail of sort of the different emissions from that planetary nebula. And so this is something that we're hoping to maybe, as we play with it some more, One of the things I have to do is kind of rotate the filter in the filter wheel so that everything's more horizontal, which is the way the frame goes, so that it gives me a little bit more room. And to kind of figure out and calibrate it so that we know exactly where the lines and things are and stuff. But this could be a really nice, simple way of us doing some spectroscopy as well. And students can kind of learn a lot from that. And it's not expensive. Okay, it's really very reasonable. Other ways of doing some research, radio dishes. I mean, it's another wavelength, my view, but I have a volunteer working at the observatory who, from her point of view, visible light is junk. And so she's all into the radio aspects of it and has basically been getting our radio dish operational. So we basically have a radio dish at the observatory. It was all but abandoned there. And so she's been working on putting in some different the detectors and the sensors and the radio and the computer processing and everything like that to get it up and running. And hopefully we're close and we can start making some activities for the students to actually do so they can actually use that dish and everything. And this is, you know, again, doing some radio astronomy is not out of the realm. It's a very feasible thing for amateurs to do. And the nice thing about radio, it doesn't matter if it's cloudy. Okay, so sometimes it might be better to do radio astronomy around here than to do visible light astronomy. Okay, we've also got some all-sky cameras up and running at the observatory, and we've mainly been having students writing some code on doing some analysis and such, but there could potentially be other types of projects that they can do utilizing the data, and we're going to try to make that available eventually as part of a database and such.